Good afternoon. Today I will present some global theorems concerning two families of surfaces. The first one is the family of compact regular surfaces without boundary. And the second one is the family of complete regular surfaces. All the surfaces are supposed to be connected. The first result I will present is a corollary of the global Gauss-Bonnet theorem. If S is a compact connected regular surface without boundary, then the double integral of the Gauss curvature over S is 2 pi multiplied by the Euler characteristic of S. If you want to prove this result, you just use the fact that a surface satisfying this hypothesis can be seen as a regular region without boundary component. So if you use the global Gauss-Bonnet theorem in this case, you get that the integral of kg t gives no contribution because there is no boundary. The sum of sine angle is 0 because there is no boundary. Then we get that 0 is equal to 2 pi q of s minus the integral of the Gauss curvature over S, which is exactly what we wrote here. Let's determine the Euler characteristic of some surfaces. So let's check that key of the sphere is 2. This can be done using any triangulation. So for example, you can do this with the triangulation in the picture. One possible triangulation is this, or another one is this. And for this one, you have that the number of vertices is 6, the number of edges is 12, and the number of triangles is just 8. So you will get that T, which is V minus E plus F, is equal to 2. Instead, in this case, we have that V is 4, E is 6, and F is 4. This means that you get again T equal to 2. If you have the Euler characteristic of a surface, you can compute the genus. The genus of a surface can be computed using this formula, 1 minus 1/2 P of S. So this formula implies that the genus of the sphere is equal to 0. Now, other examples of compact connected regular surfaces without boundary are the following. If you want to compute the Euler characteristic of these three surfaces, instead of using triangulation, you can use a generalized triangulations, which, despite their name, is a family of a finite family of polygonal regions Ti with I equal to 1 to F, whose union is the surface and Ti intersection Tj with I different from J is empty or a common edge or a common vertex. It is possible to prove that if you compute the Euler characteristic using this kind of triangulation, you get the same value. For example, suppose that you have a triangulation, a generalized triangulation like this, and suppose that you want to compute the Euler characteristic using this triangulation, and you want to show that you get the same value if you consider a triangulation made of triangles. So the idea for proving that key does not change is that you can see a polygon like this as the union of triangles. So, and what you can do is that you can compute the Euler characteristic of this new triangulation, showing it is the same. So, for example, if you replace this polygon by these 6 triangles, it's easy to see that the number of vertices increases by 1. The number of edges increases by 1, 2, 3, 4, 5, 6. And the number of faces increases by 1, 2, 3, 4, 5, 6, minus 1, which was the polygon. So this increases by plus 5, which is 6 minus 1. So it's immediate to see that the quantity V minus C plus F does not change. So this says that instead of using triangles, you can use this kind of polygons. We use now generalized triangulation for finding the Euler characteristics of this kind of surfaces. So for this surface here, we can use this generalized triangulation. Essentially, here we are using polygons and no triangle. And here you have that the number of vertices is 8, the number of edges is 16, the number of faces is 8. This implies that key is equal to 0. If you do the same with this, so you consider this triangulation here, you will see that the number of edges is 18. The number of vertices is 18. The number of edges is 36. The number of faces is 16. So you get that the Euler characteristic is -2. And if you continue, you find key equal -4. And if you observe the values of the Euler characteristic we obtain, they are negative even numbers and 0. It is possible to determine a formula for key in function of the genus. So we said that the genus is 1 minus one half key of S. So this implies that key of S is 2 minus 2G. And this says that these surfaces have respectively G equal 1, G equal 2, G equal 3. Essentially, the genus of a surface of this kind coincide with the numbers of holes in the surface. Now, here you have a surface of genus 1 having 1 hole. This is a surface of genus 2 having 2 holes. This is a surface of genus 3 having 3 holes, and so on. These are essentially all the compact connected regular surfaces without boundary up to diffeomorphism. This is what theorem 6.16 says. The genus of every compact connected regular surface without boundary is a non-negative integer and every pair of such surfaces with the same genus are diffeomorphic. So this says that up to a diffeomorphism, the compact connected regular surfaces without boundary looks like the surfaces I erased. We have now a simple corollary. A compact connected regular surface with Gauss curvature positive and without boundary must be diffeomorphic to S2. The proof is very easy. So if this is not true, then the Euler characteristic of the surface would be different from the Euler characteristic of the sphere, which is 2. The Euler characteristic of a surface of genus G is a 2 minus 2G, implies key is smaller or equal to 0. It cannot be 2, so it can be only 0 or a negative number. This implies that the integral of the Gauss curvature, which is given by 2 pi ks, would be non-positive, and this is not possible because k is positive by hypothesis. The next result I want to present is the Poincaré theorem. And for doing this, I need some definition. Let's start by definition 6.18. Let V be a tangent field on a regular surface S. So this means that V is a vector field such that for each value, for each point of the surface P, V at P is a tangent vector to the surface. We call P in S a singular point of V if V of P is 0. In this case, P is isolated if you can find a neighborhood of P which does not contain other singular points. I need also the definition in 6.19 which introduces the notion of index at an isolated singular point P of a vector field V. Observe that this definition is about vector fields in R2, not on a surface. This is equal to the degree of the following function given by f epsilon t where gamma epsilon is the parameterization of a circle oriented counterclockwise of radius epsilon centered at P, epsilon positive small, such that V has no other singular point than P on or inside the circle. The geometric meaning of this definition is the following. Imagine that you are traveling along a small loop encircling the point P in such a way you turn your body so that you are facing in the direction of the vectors that you encounter moving along this curve. So suppose that the vector field along this curve points this way, for example. And if you do this, I mean you travel along this curve facing in the direction given by these arrows, how many counterclockwise rotation you perform? The numbers of this counterclockwise rotation is given by the index. Let's make a few pictures. So if you consider the vector field of R2 given by this formula, you see that there is a singular point at the origin, and if you consider a loop around this singular point here, like for example this simple closed curve, you move along this loop and you face in the direction given by the arrows, then it's clear that you make one counterclockwise rotation implies the index is equal to 1. It's possible to see that the index can be computed by this formula also. Another example is the one where we have this vector field. Once again, we have one singular pointed origin. And in this case, if you consider a loop around the origin, you will see that in this case your body makes a clockwise rotation if you travel along this loop, because you start from this position, then the chalk moves this way. This means that you make one clockwise rotation. This means that you can see this rotation as a negative counterclockwise rotation, implies index equal -1. The third example is the one where v is given by this function. In this case, if you take this loop here, then you make one counterclockwise rotation if you travel along this curve, facing in the direction given by the vector field along the curve. So you have index equal 1 because you have one counterclockwise rotation. Last example. In this case, we have vxy equal to x squared plus y squared 0. We have once again one singular pointed origin. I don't like my picture in this case. Anyway, if you take a loop, you will see that if your body faces in the direction given by the vector field along the curve, you don't make any rotation because the vector field is constant in direction. Why? Because the second component is always 0. So no rotations implies index equal 0. Now I have to give definition of index for a surface. The definition I gave before was the index of a singular point at a singular point in the case of R2. So suppose that P is an isolated singular point of tangent field V on an oriented surface S. R containing S is a polygonal region P belongs to the interior of R. There are no other singular points in boundary of R or interior of R. Suppose that gamma is a positively oriented parameterization of boundary of R. Sigma from U into S, surface patch covering R, compatible with the orientation and let's suppose that sigma U T is the value of sigma along gamma T. Vt is V along gamma T. And phi from A, B with values in R. This is a continuous function such that phi t equal angle from sigma ut to Vt. Unfortunately, the definition is not finished yet, so I have to erase this part. So that is Vt is a positive scalar multiple of the counterclockwise rotation of sigma ut by the angle phi t. Finally, the index of V at P, the singular point, the isolated singular point, is given by I of P equal phi B minus phi A divided by 2 pi. So in other terms, the index is the degree of the angle function phi. This definition involves a polygonal region, an orientation, and a surface patch. So a priori, the value of the index could depend on these choices. It's possible to prove that this is not true. I want to show you just two examples where S is S2 and V is the vector field given by this picture, given in the picture. This vector field has two singular points. The North Pole and the South Pole. And if you use this formula, you can prove that the index is equal to 1 for both of them. Another vector field having two singular points and index 1 at both of them is the following. It's a vector field which is 0 here and here. And it's possible to prove that these conclusions are all true also in this case. Now we can state the Poincaré theorem, which says that if S is a compact connected regular surface, and V is a tangent field. Sorry, I have to write without boundary. And V is a tangent field on S with isolated, let's write another way, all of whose singular points are isolated. Then Q of S is given by the sum of indices. Let's write another way. Sum of indices of V at the singular points. So from this picture, you get again that the key of S2 is 2, because I have a vector field in both cases having two isolated singular points of index 1. So the sum of the indices of this vector field, it is equal to 2. What about compact connected regular surfaces of genus 1? Can we say something about this using this theorem? These kind of surfaces are diffeomorphic to this object. This is a torus, and we have a corollary which says that a compact connected regular surface without boundary on which there exists a nowhere vanishing tangent field must be diffeomorphic to a torus like this. So let's show that on a torus there exists a tangent field satisfying this hypothesis. For example, you can take this vector field here the picture in the book is much better than mine. This vector field that has no singular points implies k equal 0, implies genus equal to 1 minus 1/2 k equal 1, imply the surface is a torus, which is something we already know. Another example of vector field having the same property is this. It's a vector field which is constant along vertical closed geodesics. My picture is not as nice as the one in the book. So also in this case we have no singular points. Of course, the theorem does not apply to the sphere. Why? Because we have the Airy-Ball theorem, which essentially says that there is no smooth vector field No, let's say another way. There is nowhere vanishing the smooth tangent field on the sphere. So the spheres do not satisfy the hypothesis of the theorem. Sorry, the corollary. I should write corollary here, sorry. And now let's talk about complete surfaces. I want to present just two theorems. The first one is a theorem about surfaces with constant curvature. And this theorem says how a surface with constant Gauss curvature looks like. So let lambda be a real number and S a complete connected regular surface with constant Gauss curvature K equal lambda. Then we have 1 lambda is a non-negative. This has been proved by Hilbert, and this means that there is no complete regular surface with constant negative curvature. The second statement is about surfaces with lambda equals 0. Then S is a plane or is a generalized cylinder. A generalized cylinder is a surface S such that through each point P in S, there passes a unique line LP containing S, and for each pair PQ in S, the line LP is parallel to LQ. And now the statement number 3. If lambda is positive, then S is a sphere of radius 1 over square root of lambda. The last theorem I will present is a theorem about complete surfaces with non-negative curvature. Please observe that I'm not assuming that the curvature is constant. So let S be, as usual, a complete connected regular surface with K positive or 0. Then, if S is compact, then S is diffeomorphic to S2, and 2. If S is not compact, and has at least one point with k equals 0, then S is diffeomorphic to R2. Sorry, I made a typo. This is positive. K must be positive. Okay, that's all. This is my last lecture. Thank you for your attention.